In today's lesson, we're going to examine passive RLC networks. When we use passive RLC networks as filters and at higher frequencies as matching networks or impedance transformation networks. And we also might use them as oscillator load circuits. So first we'll start with a parallel RLC network. Here we place an inductor in parallel with a capacitor and a resistor. We might input a current into this parallel RLC tank and measure the voltage that develops across the tank. What we're interested in looking at is what is the admittance of this network. We deal with admittances when we're talking about parallel circuits. So we can look at this circuit at low frequencies and at high frequencies. At low frequencies, we might expect that the inductor will dominate the admittance. So our circuit would look like this at low frequencies. At high frequencies, we would expect our capacitor to dominate the admittance. And so we might ask ourselves, what happens between the low and high frequencies? And the answer is, between low and high frequencies, we come to a resonant frequency. If we calculate the admittance for this parallel RLC network, we would have y of omega is equal to 1 over r plus j times omega c minus 1 over omega l. And at resonance, we say that our frequency omega is equal to the resonant frequency omega naught. And this is the frequency where the admittance of the capacitance is equal to the admittance of the inductance, and so they cancel each other out. And all that we're left with is the resistive term. So we can say that omega naught c is equal to 1 over omega naught l, and this leads to our resonant frequency being calculated as 1 over the square root of the product of the inductance and capacitance. So our equivalent circuit at resonance is just our original current source and our resistor. All right, if we look at this in terms of impedance, and remember that impedance, z of omega, is just equal to 1 over y of omega. And we were to plot the magnitude of the impedance, and the phase of the impedance, we would see the following. At low frequencies, the impedance is small because the impedance of the inductor is very small. So we would have some kind of plot looking like this. As we increase the frequency, the impedance increases until we get to the resonant frequency, omega naught, at which point the impedance peaks at a value of R. And then the capacitor starts to dominate and reduce the impedance as frequency increases. This happens with a 20 dB per decade slope. And we say that before the resonant frequency, the circuit looks inductive. After the resonant frequency, the circuit looks capacitive. That is to say that the impedance increasing looks like an inductor, and the impedance decreasing with frequency looks like a capacitor. Now the phase shift, because the impedance looks like an inductor, is a plus 90 degree phase shift at low frequencies where the inductor dominates. At the resonant frequency, the total phase shift should be 0 degrees since there are no reactive components. And at the frequencies above the resonant frequency, we should approach a minus 90 degree phase shift. In other words, our plot should look something like this. Here we're saying that the voltage leads the current, so it looks inductive. Here we're saying that the current leads the voltage, so it looks capacitive. Next, we're going to look at some metrics that, about this circuit, about the energy storage in this circuit. Functionally, what's happening when we use these circuits is that energy sloshes back and forth between the inductor and the capacitor every cycle, and some of that energy is lost to the resistor. In an ideal circuit where there's no resistance, the energy would slosh continuously back and forth between the inductor and capacitor, and we would see an oscillatory behavior.